Hey there, my friends, welcome to Sciencing Around, and now let's cover the topic of chemistry, that is chemical equilibrium. I don't want to waste your time, but do subscribe my channel, please. In what is chemical equilibrium? Let's see. Whenever the reaction is stopped, that is, the reaction doesn't move either forward, either backwards, then it's nothing but chemical equilibrium, the equilibrium obtained between reactants and products. Now let's read what's given in the notes which I prepared right day before yesterday and especially for you guys. Now, chemical equilibrium is defined as the state when rate of forward reaction equals to rate of backward reaction. That was more genuine definition. The rate of forward reaction, we can say rate of formation of products is equals to the rate of distraction or rate of decay of the reactants. That's it. And at equilibrium, delta G is 0. What is delta G? Delta G is Gibbs free energy. It's just nothing but free energy packets obtained at the time of reaction. But since there is no reaction at equilibrium, delta G is equal to simply 0. Equilibrium can be affected by pressure, volume, temperature, and concentration. We'll talk in Le Chatelaire principle afterwards in this lecture itself. Now let's see what is law of mass action. We know law of mass at constant temperature rate is directly proportional to its active mass. Its active mass, the mass which is included in the reaction, is nothing but active mass, where we know F is activity coefficient, A is directly proportional to C, which is molar concentration. Therefore, A equals Fc, where F is activity coefficient. Now let's see what is actually chemical equilibrium. Now, in a reaction where A moles of A plus B moles of B are forming C moles of C plus D moles of D. Alright, then the rate of forward reaction is Kf into the concentration of A power its moles, that is stoichiometric coefficient, into concentration of B to the power its stoichiometric coefficient respectively, that is the rate of forward reaction. Since it's forward, these are these are reactants A and B. And in rate of reverse reactions equals to the reverse reaction constant into concentration of C raised to its own stoichiometric coefficient into concentration of D raised to its own stoichiometric coefficient. This is rate of reverse reaction, so products are involved, that is C and D. Also at equilibrium, the rate of forward equals to rate of reverse, this equals to this, so Kf upon Kr, we are dividing these two, and Kf, that is the rate of forward or the forward constant, upon the reverse constant is equals to Kc. Kc is nothing but equilibrium constant, which is equals to concentration of C power C stoichiometric coefficient into concentration of D power its stoichiometric coefficient into concentration of A to the power its stoichiometric coefficient and into concentration of B to the power its stoichiometric coefficient. This is concentration. This A is its stoichiometric coefficient, that is this small a you can see here. Now we know Kc equals to equilibrium constant, just now I told you. So we can also say that Kc equals to concentration raised to C plus A minus A plus B. You can see here right now. C plus A minus A plus B. That is nothing but change in number of moles. That is delta N. So we can say equals to moles per unit liter, that is moles upon volume raised to delta N is equal to nothing but Kc. Now if P equals partial pressure should be given, then partial pressure of A is directly proportional to its concentration. Simply, I would not say these all things. I will just say that partial pressure is directly proportional to its concentration. Its concentration, I don't know what's constant, but it's just directly proportional. So what is Kp? Kp is the equilibrium constant which is related to its partial pressure. So Kp equals to partial pressure of C to the power its stoichiometric coefficient into partial pressure of D to the power its stoichiometric coefficient upon partial pressure of A to the power its stoichiometric coefficient into partial pressure of B to the power of its stoichiometric coefficient. So Kp is pressure power delta Ng. We had Kc equals to concentration into power delta Ng, and Kp equals to pressure to the power delta Ng. And now what is the relation between Kp and Kc? You can see here in the next topic, in the next line. Kp equals to Kc into gas constant temperature, the gas constant temperature, the whole raised to delta n, where delta n equals to C plus D minus A plus B. What is C plus D minus A plus B? C plus D minus A plus B. That is change in number of moles of products, total number of moles in products minus total number of moles in reaction. So we can say the relation between Kp and Kc are as Kp equals to Kc into RT power delta n. Now here we have relation between the Gibbs free energy and the equilibrium constant, where delta G degree equals to minus of 2.303 RT log of K, where K is the equilibrium constant. Delta G degree is the standard Gibbs free energy because it's G dash, or we can say G naught. It's standard Gibbs free energy, the free energy packets. And now let's get down to the Le Chatelier's principle, the most important part of the chemical equilibrium, mostly based on logic, not much of the formulas. Whenever a stress is given to a zone in a reaction, whenever a stress is given to the zone in the reaction, the equilibrium tries to shift in the stress-free zone. Okay, fuck off. I'm just gonna tell you that the Le Chatelier principle tells us that the reaction tries to move in that direction where there is no pressure applied, there is no much concentration. It just tries to move to the direction which is free, which has not much of the stress, we can say, not much pressure, not much concentration, we can see. That's nothing but the Le Chatelier principle. The reaction moves to the direction which does not have much pressure, much volume, much number of moles, much number of concentration. The reaction avoids the place which is stressed or which has much pressure, volume, and all that stuff again. Now let's see addition of inert gases to a reaction. In a reaction, AA plus BB gives us, A moles of A plus B moles of B giving C moles of C plus D moles of D in equilibrium. Then Kp equals to number of moles of C to the power C into number of moles of D to the power D into number of moles of A to the power A into number of moles of B to the power B into Pt, which is partial pressure, you can see, upon summation of all the number of moles into change in moles, that is C plus D minus A plus B. Now just remember addition of inert gases, the equilibrium moves forward. Yes, we have to remember this thing. It's experimental stuff, I hope, as inert gases don't react to anything. Just remember addition of inert gases, the equilibrium moves forward. If delta n, that is change in the moles, are negative, then reaction moves backward. Yeah, by the relation between Kp and Kc, we can see an addition of inert gases has no effect if the volume is constant. Yeah, we know that, because if we just add inert gases but the volume remains the same, as inert gases don't react to anything, they can not even act as catalysts. We can learn that thing in surface chemistry afterwards. If temperature varies, now if the temperature is varying, we can say then log of K, that the log of the equilibrium constant at T2 temperature divided by equilibrium constant at T1 temperature, then did I write it properly? Wait, T2 T1, log of equilibrium constant at T2 temperature divided by log of equilibrium constant at T1 temperature equals to delta H upon 2.303 times gas constant into 1 upon T1 minus 1 upon T2 and nothing else. Did I say nothing else? Such a big formula and you're saying nothing else? Okay, log of equilibrium constant at T2 upon equilibrium constant at T1 equals to its enthalpy delta H upon 2.303 times gas constant into 1 upon T1 minus 1 upon T2. I hope it's quite a useless formula, but you can apply it at least somewhere. Everything is useless, you know. So now in our next page, if Kp increases, the reaction moves forward. If Kp decreases, the reaction moves backward. That's quite obvious. That's so cute. That's so sexy. Minus of delta G equals to minus of delta H plus T delta S, as we know by the formula. delta G equals to delta H minus T delta S. The Gibbs free energy equals to enthalpy plus temperature into change in spontaneity. Now according to the 1/2 equation, delta G equals to delta G degree plus RT ln of this stuff, which is nothing but Kp. Yes, you can see it here. Delta G equals to delta G degree plus RT ln of Kp and nothing else. Now at equilibrium, delta G equals to minus of RT ln Kp, where delta G degree is here, right here. So at equilibrium, delta G degree equals to minus of RT ln Kp, means minus of RT ln Kp plus RT of ln Kp, delta G equals 0. Where Kp equals to minus of delta G upon RT by those substitutions and all that stuff. Now one of the important parts, delta G is negative, then K is greater than 1, which represents forward reaction. If delta G is positive, K is less than 1, which represents reverse reaction. And if delta G equals to 0, K equals to 1, which is reaction at equilibrium. Now vapor density and degree of dissociation. It's actually the part of electrochemistry, or we can say it's the part of, volumetric analysis. Now just let's study what is this degree of dissociation. No, it's degree of dissociation is actually the topic of ionic equilibrium. Now let's see what it says in chemical equilibrium. In reaction where A gives Y moles of B, initial moles A is 1 and it's not yet formed, so it's 0. At equilibrium, we can say 1 minus x, something decreases here and this becomes yx, since y is its initial number of moles. So yx. If initial volume of 1 mole of A is V, that is if V is the initial volume, then at equilibrium volume mixture of A and B, what would be its initial volume? That is 1 plus x times y minus 1V. Now, you know what is this? We can just substitute this thing by 1 plus x times y minus x. You know what is 1 plus xy minus x? We can also tell this by this thing. That is 1 minus x plus xy. You know what is 1 minus x plus xy? Nothing but this thing, 1 minus x plus xy. 1 minus x plus xy, that is 1 minus x, this thing plus this thing, that is total number of moles into volume. Alright, 1 minus x plus xy times v, that is at equilibrium the volume at the mixture of AB, the total volume would be this thing, total number of moles, that is 1 minus x into xy into its actual volume, that is initial volume. Now we can also say that mass upon volume is density here, that is capital D. You can see right here it is the capital D. And now we can see in my next page, that is molar density equals to mass upon volume, which is by small d, that is mass m, mass would remain constant, upon total number of moles. I told you 1 minus x plus xy, total number of moles into the volume, that is volume of mixture, mass upon volume of mixture. Now the actual density upon the molar density equals to the volume, that is actually it's total number of moles, 1 minus x plus xy. So what is x? X is nothing but d after those fucking rearrangements. I don't want to waste my time on that since video is quite long. X equals to actual density minus molar density upon molar density into y minus 1. This is the value of x, where y is the number of moles of product formed from 1 mole of reactant. And actual density upon original density is nothing but Van 't Hoff factor. You will learn about Van 't Hoff factor in solutions in colligative properties, but right now I think it's okay. D by 2 is its molecular weight, D into 2, the molecular weight, and the molar density into 2 is molecular weight of the mixture. And from there we completed the chemical equilibrium. Please go through the video quite carefully. I hope you will. And please, if you like this video, please do like and subscribe my channel, because I want your support. And if you think something was wrong in my teaching method, please do comment. I'm just, I'm dying for a comment. Please do comment. So thank you guys. That was it for chemical equilibrium. See you soon. Happy sciencing.